Let's look at the proof of the triangle inequality for integrals. We're going to look at the real case and the complex case. So let f be a real function which is continuous on the closed interval a to b, then the absolute value of the integral is less than or equal to the integral of the absolute value. So the real case is very straightforward to prove. So we're going to start with this and take it as true. If this is 0, well, then you have equality all the way through this whole thing. If this is positive, well, then it's equal to its own absolute value and greater than the negative of its absolute value. And if it's negative, then it's going to be less than its absolute value and equal to the negative of its absolute value. So we're taking this as true, and all we're going to do now is just integrate all the way through, and we get this. Okay, from here, we're going to go to here using the Algebra 1 principle. If you have absolute value of A is less than or equal to B, well, then you can expand it like this, but we're going to be going the other way. We're going to be going back here. So we basically have this, and we're going to enclose this in absolute value and just keep this part, and that's what we get. So that's the real case. For the complex case, we want to, I have this highlighted because we want to definitely remember in a minute that if you have an integral of a function, that's going to be less than or equal to if you put the function in absolute value. Okay, the complex case, we're going to just define things in the usual way. Z is a complex number, which can be expressed as this, and we're assuming our integral will be a complex number. And we can get this result simply by taking the absolute value of this, because this here, so if we split the absolute values up, the absolute value of e to the I theta is just 1. So we can ignore that, and we get this. And of course, r can't be negative, so we don't need absolute value marks for it. And this is going to be, we're going to need this at the end. Okay. Now, what we're going to do is multiply through. We're going to multiply through this with e to the negative I theta. We're just going to multiply through by this thing. And so that's going to get r alone. It's going to give us this in place of this, and this in place of this. Okay, so r equals this, which equals this, which equals this. Okay, where does this come from? Well, since r is real only, then the integral must be of only the real part of this complex number. And that's where we're going to start, that r equals the integral of the real part of the complex number. And so from here, it's going to happen pretty fast. So remember from above, if we have an integral and we enclose the function in absolute value, well, then it's going to be greater than or equal to this. Okay, so that gets us up to here, and that's from what we just saw above. Okay, and then we can conclude that the integral of the real part is going to be less than or equal to the integral of the whole complex number, based on that the real part of z is less than or equal to the modulus of z. And that's pretty straightforward to think about. If you have a complex number and you have the real part, well, the modulus is going to be greater than or equal to that. Okay, from here to here, all I've done is just enclose the, I've just split the absolute value up into two parts. And this, the absolute value of e to the negative I theta is 1, just like if this were positive. So if you think of this, okay, it doesn't matter that sine is negative. If you go out, if you do your cosine and do a positive sine or a negative sine, your modulus is still going to be the same. And so this would be the modulus, and that would be 1. So we can ignore this and we just get this. And now we're there. So remember that r is less than this, and r is equal to this. So remember, this is r, and r is less than this, and we get our result.